All right, we are really embracing midterm. So we got two people here, or sorry, reading week. So I guess people have started reading week early, but we still have some stuff to cover. So this is/was going to be a fun lecture, but hopefully it's okay with two people because you'll have to help me out with all the coding stuff because a lot of it is just kind of free form. So today we will be talking even more about scheduling and page tables kind of as just review and a fun example. So we kind of talked about priority scheduling and dynamic scheduling, but we didn't see any example of it, so that's what we'll do, and it matches up to previous midterm questions, so something like this is probably fair game for quizzes and stuff like that. So this dynamic scheduling where you dynamically change the priority of a process as you're doing scheduling might also be called something like feedback scheduling. And you basically create an algorithm to manage the priorities for you, and otherwise your scheduling algorithm is pretty much the same as we saw before. So we use set time slices, and the idea here is we have interrupts every so often within that time slice, and we measure CPU usage across that time, and then we increase priorities of processes that don't use their full time slice, so that are probably more I/O bound and not CPU bound, and then we decrease the priority of processes that use their full time slice. And the idea of this is to give essentially priority to I/O bound processes so you have good responsiveness while still being fair and giving CPU bound processes a lot of CPU time so you have good throughput still. So we pick the lowest number as the highest priority, kind of what we've been seeing before and what Linux does. So each process gets assigned an initial priority when it starts, so Pn, where n is the process number. And then we're going to pick the lowest priority number to schedule, and then if it yields, we pick the next lowest number, or if there's a tie, we pick whatever came first in arrival order. And additionally, if a lower priority task, not even with this current running one, becomes ready, we would switch directly to it and just switch directly to it and let it execute until it yields or it's done its time slice. So then within the time slice, we record how long each process executes for the time slice. And in this, there are many timer interrupts during the time slice. So a time slice will be a multiple of timer interrupts. So you basically just count the number of timer interrupts that thread or process, whatever you happen to schedule, is actually executing for. Then at the end of the time slice, you update the priority of each thread with so the new priority is the current priority divided by 2 plus whatever the value however many time slices you were executing for, and then you just reset the time everything is executing for back to 0 to keep track of it for the next time slice. And the idea here is that, hey, well, this is fair because we're essentially halving the priority, so that will converge to 0. In this case, 0 is our highest priority, so we know eventually that it will run. And you could, of course, play with these numbers to get kind of different trade-offs, but this is kind of one standard trade-off you would do. So this is how it would look, and this is like the midterm question or final question, I forget which one it was, but it says, hey, we have 4 processes, and let's assume they all have an initial priority of 0. Actually, the midterm doesn't say that. You have to assume initial priority is 0, or you can assume whatever you want. There's 2 answers. So we'll first assume a priority of 0. So the question says, hey, assume we have 4 processes all ready to execute, and they arrive in order X, Y, A, B. And the question doesn't say what the arrival order is, but it should have. So between those 4 processes, A and B are CPU-bound processes, so they'll never yield their CPU time or do anything like that. And X and Y are I/O-bound processes, so they'll only execute for 0.1 seconds, and then they'll block for 0.5 seconds. then the question says, hey, okay, so we have timer interrupts every 0.1 of a second, and then each time slice is a full second. So if you divide those two numbers, each time slice is made up of 10 timer interrupts that we have to keep track of. So in this question, it says, what is the scheduling? And each box here represents a timer interrupt. So what's going to be the first thing we execute? If they all have the same priority number and their arrival order is X, Y, A, B. Anyone in class? X, right? It's the first one that arrived. They all have the same priority number, so you just do arrival order. Yeah, we got X in chat. We got 2 X's, lots of X's. So we'd schedule X first. So it only runs for 0.1 seconds, and then it yields and would block. So after it's 0.1 seconds after the next timer interrupt, we would switch to the next task because this one would be blocked. So what would we switch to? Y. So we would switch to Y, and Y would execute for the next time slice. Now, Y is done, and we have to pick a new process to schedule. So what should we pick? A. How long is A going to run for? So A could either run all the way to the end of the time slice, or X here went to sleep after the first time slice. So it blocks for 0.5 seconds. So within 5 time slices after X goes to sleep, it would be ready again. So if we assume that, hey, we should just schedule that because it is a high priority one, we would go ahead and schedule X when it wakes up. But in this case, it's not higher priority, so whenever X becomes ready, kind of at 5 time slices or 5 timer interrupts after it goes to sleep, we wouldn't schedule it because it has the same priority as A, so we'd only schedule X in if it had a higher priority. So in this case, A would just execute for the rest of the time slice because they all have the same priority. And it was already executing, so by the time X becomes ready, it's going to, when X becomes ready at time 6, we don't switch to it because it's the same priority as A, so we're not going to switch to it. And then similarly, at 7, Y is ready because it just blocks for 0.5 seconds, but we don't schedule it because it's the same priority as task A, so we wouldn't bother scheduling it. So at the end of our time slice, which is at time 10, we would recompute the priorities of everything. So the priorities of X is its current priority is 0, so we divide that by 2, get 0, and then add however long it executed for in terms of number of timer interrupts. So it executed for 1 timer interrupt, so its new priority is a 1. Process Y, same deal, it also executed for 1 timer interrupt, so its new priority is 1. And then process A executed for 8, so its new priority is 8. And then process B executed for 0, so its priority is 0. So at T10, we get to schedule something else. What are we going to schedule to execute? B. B is the lowest priority. Nothing comes close to it, so B is just going to execute for the entire rest of the time slice. So this is what our schedule is going to look like. It would just be X, Y, A, and then B for the remainder of the time. Okay, so let's do the same thing, except now A and B have an initial priority of 6, and X and Y's priority are 0. So if we have this case, well, X and Y have priority 0, A and B have priority 6. So at the beginning, what are we going to schedule? Again, they're already in the same arrival order. X again, right? It was the first one there, and it's also the lowest priority. It's tied with Y, so between X and Y, X came first. So we'd schedule X, then X yields and blocks for 0.5 seconds. So we don't have to worry about it until the end of the 6th time slice. So then we would execute Y, and then it would go to sleep. Now instead, when X becomes ready, because it has a lower priority, we would switch back to X from A. So now A would execute, we'd pick A because there's a tie between A and B, so we'll just pick A. And now at T6, X becomes ready, and because it has a lower priority, we would just go ahead and immediately switch to it. So now we immediately switch to it. Hello. We immediately switch to it, and then at the end of the 7th time slice, Y becomes ready, so we would switch to it because it is still a higher priority than A or B. And then they're both blocked at that point, so the only thing we can schedule is A or B, and we still pick A. Then at time 10, so the end of the time slice, we recompute the priorities again. So X and Y had an initial priority of 0, so 0 divided by 2, plus however many timer interrupts that they were executing for. So the priority of X and Y are going to be 2. The priority for A is going to be 6 divided by 2, which is 3, plus 6, so its priority is 9. And then process B is going to have a priority of 6 divided by 2, which is 3 plus 0. So now, at this point, we have to pick something to schedule again. So what are we going to pick to schedule at this time instant, at time 10? So X, we got an X and a B. So in this case, X we can't schedule because it is essentially asleep until 1, 2, 3, 4. It's back like here. So X isn't schedulable, Y is not schedulable. And between A and B, B has the lowest number, so it's a higher priority. So we'll go ahead and execute that for 2 time units. And then after that, X is ready again. And X still has a lower priority than B, so we would switch to X. And then Y becomes ready, and then for the same reason, we would switch to Y. And then after that, they're both blocked, so now we just have to pick between A and B, and we would pick B again. So B would execute for another 4 timer interrupts, and then X is ready again, so we'd switch back to X, and then switch back to Y. And then this is what our schedule would look like. So any questions about that? Nope, we're good. Okay, so this would be a little bit of a different question if A and B had priority of 4 instead of 6, in which case I guess I'll leave it up for you to argue about. But if A and B had priority of 4 instead of 6, then B would execute for this entire time slice because it would have the same tied priority as X and Y, so you wouldn't switch to it when they become ready. Okay, any questions about that? Cool. So I guess before we get to the fun stuff, oh yeah.
How does this collaborate with the process priorities, like we set the number manually?
So the question is, how does this work with setting the number manually and just static priorities? So this is dynamic priorities, so it's just a different algorithm. So you can initially set the initial priority, but the algorithm will dynamically change the priorities. So you get kind of good interactivity with IO-bound processes and more throughput with CPU-bound processes. Okay, so another thing we could do, another question that's on the midterm for this same schedule is, hey, what if it was round robin? So we can do that really quick. So if this was round robin instead, initially we'd have X, Y, A, and B. So we would schedule X, and then at the end of it would go to sleep after 1 timer interrupt, so it wouldn't be schedulable. So our queue would look like this, YAB. So we would schedule Y, And then whenever we schedule Y, what's in our queue is A and B. So this is round robin, so we're just picking whatever's at the front of the queue. So then we would schedule A, and then at the end of that, whenever A is done, so this is round robin, and you're just going to change every timer interrupt and just go through all the processes. So A would execute for one timer interrupt, and then it would be sent to the back of the queue because it's still able to execute, it doesn't block or anything. So you'd get X, Y, A, B, and then here you would have A, B in your queue. So you would have A, and then again, you would have B, A after that. Then you would schedule process B. And then at this point right here, X is ready again because it's been 5 time units. So what we always do is we put B, whatever task just gave up its time unit, if there's any ties, we put it at the very back. So right before when X is ready, our queue would be A because it was still in the queue before. And then after A would be X, the newly ready one, and then B would be after that. So at T7, we would schedule A, and then our queue would look like X, B, and then at this time unit, Y is ready again. So when Y is ready again, we would throw it at the end before we reschedule B or A at the end. So now our queue would be X, B, Y, A. So we would schedule X. It runs, and then it gets blocked. So now our queue is B, Y, A. We would schedule thread B. Then we would have Y, A, B in our queue. And we would schedule process Y. And this would go on and on like this. For the question has you do this for another time unit, but it's going to be the exact same thing. So it's just the exact same thing, but longer. All right. And that was round robin. So any questions about that before something hopefully more fun? Okay, so more fun. So we'll explore multi-level page tables live. And there's only like 4 people here and 3 in chat. So hopefully this is okay. So I essentially just wrote an MMU simulator. And if you want to play with it yourself, you can go into this lecture 23 directory in your examples and just build it using those commands. And there's an MMU sim command. So let's go ahead, play with that a little bit. So, oops. So here is our MMU simulator. So right here, so how the MMU simulator works is it has a root page table, and we're going to assume that SV39 kind of multi-level page table format, and we will resolve all the virtual memory addresses. So there's this function that says allocate page table. Allocate page table will return you a page. So it will be 4 kilobytes, and then you're free to do whatever you want with that page. So first, we allocate a page that we're going to use for our L2 page table. So that's our highest level if we're using SV39. And we would set that to our root page table because essentially our MMU is just going to use the root page table to go ahead and resolve whatever the virtual address is to a physical address. So we set the root page table to empty page. So none of the entries are valid, none of them point to anywhere. If we tried to resolve anything just using this as our root page table, they would all be page faults. So what we're going to do is try to resolve the address ABCDEF. So if we want to craft our page table and actually make it resolve to something, so let's try and make it resolve to Cafe DEF. So if we do that, then, so how we do that is if our address is ABCDEF, well, This part, because it's SV39, this would be our 12 offset bits, because remember each hex character is 4 bits. So 3 of them is 12 bits, which is the size of our page. So this would be our offset. So whenever we're translating, we don't touch those. We'll be translating ABC to essentially point to some physical page. So if we want to know what indexes to use, well, unfortunately, there's only 9 bits, not 8. So it's easier if we just write it out in binary. So if we write ABC out in binary, starting from the end, it would be 0, 0, 1, 1, because this is C, as it is up there. B would be 1, 1, 0, 1, which would be B. And then A would be 0, 1, 0, 1, which would be A. And then everything else would have zeros appended to the front. So it'd be like zeros. So we just have a bunch of zeros for the remaining numbers. So if we divide it up, and then remember, because all of our index bits in this are going to be 9 bits. So if we take a group of 9, this is our index for L0, because it's the lowest 9 bits. And then if we go ahead and count the next 9 bits, 1, 2, 3, the next 9 bits would be here, and this would be index of L1, and then 1, 2, 3, 1, 2. So 1, 2, 3. So all the other padded bits up here would be the index of L2. So if we want ABC, EDF to resolve to a virtual address, we know what indexes we have to use. So if we convert index L1 back to just decimal so we can read it, that 1 is a 4. It's 4 plus 8 plus 16 plus 32 plus, what's that, 128. And if you add that all together, it is 188. And then for L1, our index would be 1 plus 4. So we need to have an entry at index 5. And then for L2, it's just a big old 0. So if we want to resolve this, so we want to resolve, this is our virtual address here. Say we want to resolve it to physical address, CAFE, and then the offset would not change. So it would look like this. So now, this is our offset. We want to resolve it to that. So in that case, we would need to have our L2 page table, which would be our root page table, would need an entry at index 0. So it would need a valid entry at index 0, and it would need to point to a L1 table. Now, if we want to resolve this, we need to make sure that there's an entry at index 5. So there must be an entry at index 5 that points to an L0 table. And then in the L0 table at index 188, then we want the physical page number because that's our lowest level, so we're going to use that for translation. So instead of pointing to a page, we know that it would point to a physical page number, and in which case, if we want the address to resolve to CFE, then the physical page number would have to be CAFE. Everyone agree with that? So let's do that then. So that's exactly what I do. So I allocate page table, just gives me a page. And because it's a page table, and I know I'm using it as a page table, I don't have to worry about offsets within that because I'm essentially just using the index to get the using the index because I know how many entries there should be. So for the L2 page table, I make an entry at 0, and I make it, so PTE from page table, all that does is essentially grabs, so the page table is a page, so allocate page table guarantees that the last 3 hex digits are all 000, like it's all aligned to a page. So PTE from page table would just essentially just get the physical page number from that, and in the PTE, one of the bits says that that is valid, so that's all it's going to do. So PTE from page table essentially just gets the physical page number of the page table, and that's just shifting by the number of offset bits. So we're just getting rid of the offset, and then that's our physical page number. And then if we have a physical page number, well, if you look at the format of a page table entry, there's 10 bits that are meant for all the permissions and everything like that. So we just shift it by those 10 permission bits, the physical page number by the 10 permission bits, and then we set the valid bit. So for this, we're only going to care about the valid bit. A real implementation would actually care about like read, write, execute, things like that. But we'll just set the valid bit, which would be bit 0 in case you're interested, and that's return the page table entry. So we create an L2 page table, and then we create an L1 page table, and then we make sure that index 1 of that L2 page table points to the L1 page table that we just got back, in this case from the kernel or the operating system or whatever gives us our pages. So after that, we need an L1 or L0 page table. So we need an L0 page table, so we'll allocate another page. So now we have 3 pages, and then we're going to make L1's entry for 5 point to the L0 page table in the same way we made the L2 point to L1. So we're going to do that, and then in the L0 page table, that's where we put our entry in the right spot. So again, we said that should be at index 188. So if we get the page table entry, that represents CFE, CAFE, then that would be able to go ahead and resolve in the MMU whenever it does the translation. So if we use the MMU now with the root page table, so it's just going to use the root page table and follow it around. If we go ahead and use that now, when we actually run this, we should see that, hey, A, B, C, D, E, F resolved to C, A, F, E, D, E, F. Okay, so that's cool, it works. So what if, anyone tell me what this might resolve to? Will this resolve to an address or be a page fault? Yeah, I just changed it to 0. Yeah, I just changed the last hex character of the address to a 0 instead of an F.
Yeah, I mean, the physical address is also going to be like.
Okay, but I'll still get a physical address and it'll look kind of like that. Okay, so we have a page hit. The physical address is going to be mostly the same, but just have that change. Everyone agree? Okay, so if we compile that, yeah, so if I do that, it would actually resolve because I'm just changing the offset. The virtual page number is the same. I'm using the same root page table, so it doesn't have to do anything special. If this would actually be as well cached in the TLB, so it would have this translation already. So if I access anything on the same page, it's the same translation, so it wouldn't translate it again, which is what we saw before. And it doesn't matter if it's anything on the same page, it would still resolve. So ABCD or ABC 000, that would still resolve to the same address or the same physical address. There would be an entry there. Okay, well, any questions about that?
Does the page table stay in the same memory device as the other processes?
So the question is, does the page table stay in the same memory space as the programs? So the page tables would be in kernel space, so the processes aren't allowed to touch them. So the kernel manages all the page tables in this. I'm just kind of simulating it. But in the real kernel, the kernel is the only one that it can swap the page tables. So essentially, the kernel is going to manage all the page tables, and then when you swap processes, it'll swap this root page table, and then that will essentially switch address spaces. So
So the MMU is actually like blocking the CPU from accessing the address and do it itself?
So the MMU is just doing the translations. So the
Like in this way, both CPU and MMU are going to use the memory bus. Okay.
So the MMU is part of the CPU. Yeah, so the MMU, all of its job is it's on the CPU, and all its job is to resolve virtual addresses to physical addresses. And then the CPU would go ahead and issue whatever memory stuff it needs to do. Okay, well, in this case, I'll leave this to you then. So say I'm just going to access address 7FFF, FFF, FFF. So if I try to translate address 7FFFFFF, which is essentially all that is all 39 bits are set to 1. So all 39 bits are set to 1. And right now, if I compile that and run it, I would expect to have a page fault because I don't have any translation for it. So if I run that, I get a page fault. And why? Because first it's going to look at the root page table. Anyone want to tell me what index spot it's going to look at in that table? 7FF. So 7FF is 7FF is too many bytes. It is 11 bytes, or 11 bits. So if everything's a 1 and all of our indexes are only 9 bits, it would be 1FF, which would be, it's looking at index, essentially the last one, which would be 511. So first access is going to be to index 511, and it doesn't have a valid entry in it because we didn't put one in it. So it's not going to resolve to anything, so we're going to have a page fault immediately. So if we wanted to, we could create another L1 page table. Oh yeah, okay, chat got it too. There we go. So if we create another L1 page table, well, we create another L1 page table, and then our root page table is that L2 page table. So L2 page table, if we want to start resolving this, we need an entry from 511, and then it would point to our L1 page table 2 that we just allocated. So now it's pointing to a new one. Again, this is still going to be a page fault. What the hell did I do? Oh, whoops. PTE from page table. So I have to put in the right format, sorry. So this is still going to be a page fault because I resolved the first one. I made it to an L1 page table, but then that didn't have an entry. So I couldn't resolve it. but I got a little bit closer even though the end result is I still have a page fault. So I need a L0 page table for this now. So if I have an L0 page table, then my L1 page table that I just made needs to have an entry of 511 that points to the one that I just made. So PTE from page table, L0 page table 2. So now it's pointing to the new page table. I'm a step closer because now I've resolved 2 levels of page table, but now in that new L0 page table, there's no entries. So again, if I go ahead and compile it and then run it, it's still going to page fault. So the way to get it to not to page fault is I need to make an entry in my L0 page table 1 of, again, my index is going to be 511, and I would need a page table entry from physical page number. What physical page number do I want to use? Anyone with any suggestions? This could be anything, any fun numbers? What about, that's fun. So if I do this and compile it now, yeah, we got beef, we got dead beef. So if I compile and run it now, what am I going to see 777 FFFFF get, or sorry, does 7 FFFFFF get resolved to? Yeah, so it's going to be dead beef. So it's going to be dead beef, and then I'm going to use the same offset there. So the same offset in 7 FFFFF is the last 3 digits, so I'm going to get those 3. So I'm going to get dead beef and then 3 extra Fs at the end, so I'll have a total of 4 Fs. So if I run that, I go ahead and I resolve it to dead beef. So, yeah. Any questions about that? Or anything, other things you want me to do? So yeah, you can see here 2 kind of different scenarios and how many page tables you might need to have to essentially translate some virtual addresses. So best case with 3 page tables, so if I only have 3 page tables, I can translate up to 512 virtual addresses if they all fit in that L1 table if it's all full. If I was unlucky, well, then I would have my 1 root page table, but for those, say I had 512 page table entries again, I could be unlucky and they're super spread out. So if they're super spread out, that means all of my L2 page tables, my L2 page table would be full of entries, and each would point to another page. So it would point to 512 pages, and then each of those page tables would have to point to an L1, so thered be another 512 pages, and to resolve, and then each of them would have a single entry. So that's kind of best case. To translate 512 addresses, I would need 3 page tables, and then worst case, I would need 1 plus 512 plus 512. So I need, 1,025 page tables to translate all the addresses. All right, any other questions while I'm here and you can play with this? Because virtual memory is like the hardest thing to wrap your brain around. So let's see. So here too, if I wanted to, well, if I want both of those virtual addresses to point to the same page, well, all I would have to do is, so say I want both of my virtual addresses, assuming they have the same offset, which they don't. So let's change this one. So let's make both of our things have the same offset. So if I want them to resolve to the same physical address because they have the same offset, all I do is make their page table entries point to the same thing. And then when I compile it and run it, they're going to resolve to exactly the same address. So I would have two ways to refer to the same memory location. So essentially I'm sharing pages. This could be done in the same process. It could be across different processes. It's up to the kernel to decide and manage all these page tables. And yeah, this is all on GitHub, so you can play with it and understand it. All right, nothing else? So thanks for the people that showed up today. So just remember, I'm pulling for you.